Hey everyone, in today's video we've got some double integral theorems that we want to talk about. Now, in the last video we talked about how we could perform an iterated integral such that if I had a double integral over a region of a function with respect to some area element, and that was a function of x and y, and I knew the rectangle that I'm integrating over, to define that rectangle as a Cartesian product, R is equal to AB with CD, then I could write that integral as the integral between A and B times the integral between C and D, f dy dx. Or I could write it equivalently as the integral between C and D times the and then inside that the integral between A and B of f with respect to x and then with respect to y. Well, now we want to relate these, and we do that through something called Fubini's theorem. Now, Fubini's theorem is a very important theorem in multivariable calculus. It allows us to perform these double integrals in ways that are suitable for our needs. So the way that we can deal with that idea is by looking at the problem statement, but note that this theorem is incredibly involved to prove, and it's beyond the scope of this course right now, but maybe we'll do that in a later video. So given that we have a region such that R is defined by the ordered pairs x and y, such that x is between a and b and y is between c and d, then we can take the double integral over the function, over the area, as either the integral between a and b, integral between c and d of f of x, y, dy, dx, or the integral between c and d, integral between a and b, f of x, y, dx, dy. So this is important because in your integrands, you might have functions that are trickier, and the trickier functions might be with respect to one variable, or they might be with respect to another variable. So you want to pick which of these you do strategically. If the x bounds are going to give you an easier time with the next integral or your first integral, then you're going to want to choose the other. Then you're going to want to choose those bounds, because in the other case, it might be harder for you to perform the integral. So there's usually an easy way and a hard way. So you need to be strategic when you're picking which bounds you go with using Fubini's theorem. Let's try an example. Let's evaluate the integral over the following regions such that R is the set of ordered pairs with x between 1 and 2 and y between 0 and pi. We want to integrate over the region y sine of xy dA. Now to do this, what we're going to do is we are going to perform the integral as an iterated integral, but we are going to choose to integrate with respect to y first. So we get the integral between 1 and 2. We can integrate either. We can integrate with respect to y then x, or we can integrate with respect to x then y. We actually want to integrate with respect to y and then x. That's going to give us with respect to x and then y. That's going to give us an easier time. So if we try that, we get if we integrate between 0 and pi, then between 1 and 2 of y sine of xy dx dy, we get the integral between 0 and pi times of the negative cosine of xy integrated between 1 and 2 with respect to y. We perform the fundamental theorem of calculus. We get the integral between 0 and pi, cosine of 2 pi minus cosine of y with respect to y, which is equal to negative 1/2 sine 2y plus sine of y evaluated between 0 and pi, which is equal to 0. Now you evaluate the other integral and you get the same thing. That's basically Fubini's theorem in action right there. Now I'd also like to discuss independent functions. Now there are some special cases where our function of x and y can be defined as a product of functions of single variables. So we could get f of xy equals g of x times h of y. Now if we want to integrate this over a region defined by a Cartesian product, we get the integral between c and d, the integral between a and b of g of x times h of y dx dy. Now obviously, because h of y doesn't depend on x and it won't be relevant to the integral, we treat it as a constant. So we can throw that outside of the integral. We get the integral between c and d of h of y times the integral between a and b, g of x dx, and then dy. So now what we're able to do is we're able to separate all of this such that we get that the integral over our region is equal to the integral between a and b of g of x dx times the integral between d and c, or c and d, of h of y dy. So we've been able to separate these, and that makes things a lot easier when we can separate our function into a product of functions of x and functions of y. Okay, so let's try an example such that r is equal to the Cartesian product of 0 comma pi over 2 times 0 comma pi over 2 of the double integral of sine of x times cosine of y dA. So exactly, we can separate this out, stopping there. We get the integral between 0 and pi over 2 of sine of x dx times the integral between 0 and pi over 2 cosine of y dy. So now we are prepared to perform fundamental theorem calculus on both of these guys separately, and then we multiply them together, and that gives us the final answer, 1. So that is Fubini's theorem and independent functions for double integrals over rectangular regions. In the next video, we're going to briefly cover average value, and then we are prepared to move on to general regions. So we've been dealing with rectangular regions, then we want to deal with general regions, right? All right, so we'll see you in the next video. Thanks for watching.